Hello students, welcome to M-10.Shala. This is Dr. B. A. Muralidhar from the Department of Textile Technology, AC College of Technology, Anna University, Chennai. We will be deliberating on shuttle-less looms today. Before we go into the details of shuttle-less loom, let us first understand as to what is the actual problem with the shuttle loom. In the conventional shuttle looms, the shuttle performs the function of holding, transporting and laying a predetermined length of weft yarn across the fabric width as it traverses from one shuttle box to another across the width of the loom. This whole process, from the mechanical point of view, is accomplished by considerable energy dissipation, as the shuttle has to be accelerated rapidly and must be decelerated abruptly. Further, other limitations associated with the conventional shuttle looms are the requirement to frequently replenish the small weft package which is kept inside the shuttle, and the limited scope to increase the loom speed, and the very high noise levels which are generated by the shuttle looms. And let us understand as to what is the principle used in weft insertion in shuttle-less looms. In view of the preceding considerations, the unconventional shuttle merely performs the function of carrying a pick of weft unwound from a stationary cone across the warp shed. In order to accomplish the above function, the weft carriers were considerably reduced in size and mass. This further led to reduction in the shed depth and the sweep of the sleeve. By adapting these modifications, it became evident that the loom with unconventional weft insertion system would run at much higher speed, giving higher productivity and produce superior quality wide width fabrics. These unconventional looms are generally referred to as shuttle-less looms. Commercially manufactured shuttle-less looms are generally classified based on the type of carrier and its passage across the shed. The carrier may either be fluid or solid, and its flight may be guided, positively controlled, or absolutely free. Now let us get into the mechanism of weft insertion by a projectile loom. In the projectile weaving machine, the entire concept of picking is different from the conventional picking mechanism. Here, the weft is inserted by a much smaller bullet-like shuttle or carrier, about 90 mm long and weighing approximately 40 grams. This element is denoted as either a gripper or projectile. The gripper or projectile draws the weft into the warp shed directly from a large cross-wound package, and a metal torsion rod propels the gripper through the shed. The torsion bar is made out of a special metal and is twisted to store energy required to propel the gripper projectile. The speed of the projectile is entirely dependent on the torsional angle of the torsion bar. Projectile can be accelerated from rest as it enters the reed space and follows a specific path created by the rakes within the warp. These rakes prevent the projectiles from flying out of the shed. The main parts of the picking mechanism include a torsion bar A, picking shaft labeled B, picking lever labeled as C, picking shoe labeled as D, picking shaft lever labeled as E, toggle plates labeled as F, picking cab labeled as I, as shown in figure 1. On rotation of the picking cam I, in the clockwise direction, the cam nose slowly displaces the roller G, turning the toggle plate F in the clockwise direction about its center O. In doing so, the toggle plates and the link H are extended, thus twisting the torsion bar A through the picking shaft B. Further, as the picking cam I continues to rotate, the cam nose will lose contact with the toggle plate G, and the cam roller R runs onto the curved part of the plate F, causing the system to collapse, thus causing the twisted torsion rod A to release the torsion, accelerating the gripper projectile P through the picking shaft B, picking lever C, and picking shoe D. Following this, the picking lever is brought to rest by the oil brake L. The beat-up mechanism in the projectile weaving machine is different from the conventional looms. Here, the sleigh is positively rocked about its center by matched cams. The sleigh carries a reed and a number of projectile guides. During beat-up of the weft, the guides move down from the shed and lie below the fell of the cloth. Now let us get into the mechanism of the weft insertion by a rapier loom. In a rapier loom, the weft insertion is carried out by a rapier device in which the weft thread is held at its tip by a carrier rapier and transfers to the receiver rapier. Mr. John Gabler is regarded as the father of modern rapier. Rapier weaving machines are broadly classified based on the type of rapier. That is, if the rapier is a rigid rod, it could be a flexible metal, it could be plastics or bands. Then depending upon the number of rapiers, method of weft insertion, and the positioning of the weft insertion mechanism. Now let us get into each and every classification. The insertion of a double pick. In this technique, the weft yarn is threaded through a hole at the tip of the rapier and is widely used in tape and carpet looms. With this technique, conventional selvages are formed on the weft supply side, while at the other side the selvage is formed by either a catch cord system or by a knitting. Insertion of single pick with single rapier. During the loom cycle, in this process, a single rapier is inserted across the whole width of the loom shed and then withdrawn. The weft yarn is either inserted during the rapier insertion or rapier withdrawal. The main advantage of the system is that the problem of weft transfer is avoided. However, since the rapier has either idle forward or backward movement, the loom speed is comparatively slower than other rapier looms. Let's talk about the two-phase rapier. In the two-phase rapier looms, the rigid rapier is driven from the center and has rapier heads at each end. In one cycle, the rapier inserts one pick alternately in the right and left hand fabric, and beat up in opposite phase occurs. Now let us get into the double rapier weft insertion with loop transfer, which is also called as the Gabler system. In the double rapier system, two rapiers enter the shed from the opposite ends, and the weft yarn is transferred from one rapier to the other when they meet at the center, and thereafter they are withdrawn. Thus, both rapier insertion and withdrawal is used for weft insertion. With a single weft supply, the weft may be introduced as a loop into the middle of the loom, and upon transfer to the other rapier, the transferred loop is straightened out during rapier withdrawal from the shed. So the next system is the weft insertion principle by gabler system. In the gabler system, the weft is supplied from cross-wound packages placed on the right side of the loom. The weft is inserted by two flexible rapiers in two-pick weft insertion cycle to form a smooth and uniform conventional selvage at right hand side of the cloth and an unconventional lino selvage at the left hand side. The cyclic operation of weft insertion is shown in stages in figure 2 from A to I. Figure A has shown that both the rapiers are about to enter the shed. The weft is correctly positioned and the end of the weft is firmly held by the gripper G. In B, you can see both the rapiers have entered the shed. The weft depressor F has moved back and the rapier is drawing weft directly from the package. In position C, we can see both the rapiers meet at the center of the loom and the loop is about to be transferred to the receiver rapier. Further, the weft clamp is closed to stop weft supply from the package. In position D, we can see the free end of the weft is drawn through the remainder of the shed. Simultaneously, the depressor moves back for the next pick. At E, the pick is fully inserted. And at F position, we can see the beat up of the weft is completed and the rapier advances towards the shed. In position G, the rapier enters the shed and the weft is slipped off the weft guide components I and J. In H, you can see the weft is cut by the cutter H and both the rapiers meet at the center. In position I, we can see that the transferred loop is again straightened during the rapier withdrawal. In this way, the second pick of the cycle is laid. Now let us discuss the double rapier weft insertion by tip transfer, also called as the Devas system. In this system, the weft is transferred directly from one rapier tip to the other rapier tip. For this system, a yarn clamp is required on the head of both the rapiers. Alternately, in other systems, the yarn clamp is transferred from one rapier to the other rather than the weft yarn being transferred. The principle of weft insertion in Devas system is shown in figure 3. In the Devas system, the supply packages are mounted separately. The weft yarn passes through the thread eye B and the weft tensioner C. The weft yarn further passes to the vertical selector needle. The number of needles depending on the number of weft colors being used. The downward movement of the needle places the weft yarn at rapier level and is selected for pick insertion. The weft insertion cycle operation is as follows. In position 1, the needle presents the weft to the advancing rapier, which grips the weft as it enters the shed. At position 2, the previous pick, which is still connected, is cut off by the knife blade. At position 3, the rapier, that is the right side rapier, continues to move and reaches the center of the loom a little earlier and is opened by opener lever H. At this point, the left rapier inserts the weft yarn into the opened right rapier. As soon as the weft yarn is secured by the right hand rapier, the rapier withdraws from the shed, drawing the weft from the package. After reaching beyond the selvage, the weft is released. In this way, the weft insertion cycle continues in the Devas system. Now let us deliberate on the fluid mechanism of weft insertion by air jet loom. In an air jet loom, the weft yarn is inserted pneumatically using compressed air flow through the shed by the main and relay nozzles. Weft insertion by air and water jet looms offer considerable advantages such as low noise level and its ability to weave wide range of fabrics at high weft insertion rates. In the air and water jet looms, the energy is stored by compressing them and releasing some of this energy to propel the weft across the loom. As the weft yarn to be carried across the loom weighs a few milligrams, the weft propulsion attains high velocity within a short time. Air jet loom offers more practical and lucrative solutions because of air's low density and high availability. The working principle of the commercially available maximum Murata air jet is outlined below. A typical sequence of weft insertion on an air jet loom is as follows. The weft yarn A is measured by a measuring drum B equivalent to the cloth width is inserted into the shed by nozzle D, which sprouts the weft yarn across the loom by compressed air. After picking, the slack yarn is drawn back. On the other side of the loom, the suction tube H guides the inserted weft and inhales. The weft insertion cycle is depicted in figure 4 A to F. In position A, the positively drawn out weft is measured by the measuring drum B. At position B, on weft insertion, the needle J catches the weft yarn on the other side of the loom. At C, the weft thread straightener C draws back the weft yarn which has been sprouted beyond the cloth edge to take up the weft slackness. At position D, the rotating measuring drum winds the weft. The straightener retracts the weft back to the cloth edge. The reed moves forward and the air jet nozzles now has stopped sprouting the weft. At position E, at the time of beat up, the cutter E on both sides of the cloth cut the weft yarn about 6 mm to the edge of the cloth. At F, the cut weft yarn hangs down the nozzle. At this point, the straightener moves in and draws back the weft yarn to the nozzle tip. The air jet loom requires quality compressed air of about 5 bars at the inlet of the loom and about 7 bars at the exhaust point. Moisture in compressed air must be eliminated in all cases, as moisture leads to corrosion of metallic parts, obstructs the flow of air by adhering to foreign particles, and further it tends to produce tiny holes on the pipeline leading to air leakages. Traverse aid for maintaining airflow. The speed of the air along the line of the nozzle, which is the pick path, falls rapidly beyond the orifice. One way to overcome this is by means of a multi-ring confuser mounted on the sleigh, as shown in figure 5.2. The confuser moves in and out of the sleigh for every pick. This makes it difficult to weave heavy weave fabric density. As such, to overcome this problem, profile reeds were developed which act as an air guide and are more commonly used in modern air jet looms. Whereas deliberate mechanism of the weft insertion by a water jet loom. The weaving principle of a water jet loom is similar to that of an air jet loom, the only difference being that water is used instead of air. However, only hydrophobic yarns can be used in weaving on these looms. Moreover, the loom operates on only one nozzle, thereby limiting the fabric range and fabric width that can be woven on water jet looms. The water jet loom is the least flexible as the range of fabric woven is limited to medium weight and the yarn must be hydrophobic. Further, The maximum width of the loom is restricted to 230 centimeters, thus leaving little flexibility in the dynamic clothing market. However, the water jet looms are best suited for manufacturing 100% synthetic fabrics, and these looms are least noisy and require the lowest energy to operate on. The weft yarn from the cone or cheese passes over a guide roller and through the tensioning device to the measuring drum. From there it passes through a cramper or a gripper to the picking nozzle. The cramper or the gripper regulates the insertion of weft in the shed. Weft insertion on a water jet loom depends on many factors such as the quality of water jetted out of nozzles, the water pressure, the nozzle cross section, the opening and closing of the cramper with respect to the water jetting angle, the measuring length of yarn, and the nozzle position. So students, let us conclude this module on shuttleless views. As we briefly looked into the features of the shuttle and the shuttleless looms at the beginning of this module, some of the inherent drawbacks of the shuttle looms which led to the development of the shuttleless looms, and then how the different weft insertion techniques have been used in the shuttleless looms. So let us briefly sum up the topic. In this module on shuttleless looms, we have deliberated on the weft insertion principles of the unconventional looms. The unconventional looms commercially manufactured in the industry are the projectile loom, the rapier loom, the air jet loom, and to some extent the water jet loom. And we have seen the different principles used in the above looms very briefly. Thank you.